Ok, boa tarde, todos e todas, good afternoon, everyone. Nós estamos aqui no nosso seminário número 57 e, dando continuidade essa tarde, temos o professor Cesar J, do Departamento de Matemática Aplicada da UFRJ, que vai ser apresentada pelo nosso colega, professor Mauro Rincon. Por favor, obrigada.
Obrigado, Sandra. Bom, é um grande prazer apresentar aqui um colega do Instituto de Matemática, da Universidade Federal do Rio de Janeiro. Vou apresentar aqui o Cesar Javier Nietzsche Mazeu, conhecido como Cesar Nietzsche. Ele tem graduação e mestrado pela Universidade de la República do Uruguai, terminou em 2000, depois fez doutorado pela Universidade University of California, Santa Cruz, nos Estados Unidos, em 2006. Fez pós-doutorado no IMPA entre 2006 e 2008. Atualmente é professor do Instituto de Matemática do UFRJ. Ele começou em 2013, até o momento ele é professor nosso. Ele foi vice-coordenador da pós-graduação de 2016 a 2018 e coordenador da pós-graduação do Instituto de Matemática de 2018 a 2020. Ele trabalha na área de EDP, mecânica, mais especificamente mecânica dos fluidos, e em sistemas dinâmicos hamiltonianos e geometria simplética. O César é revisor de mais de 20 periódicos, ele já publicou mais de 20 artigos, orientou 3 dissertações de mestrado, uma tese de doutorado, 10 orientações de iniciação científica, sendo que dessas 10, 3 foram premiadas na jornada de iniciação científica da UFRJ. E o título da palestra do César hoje é Decay in Sobolev Critical Spaces for 3D Navier-Stokes-Coriolis and Navier-Stokes Equation. Segue com você agora, César. Obrigado pela presença.
And I will speak in English, if you don't mind, because there may be audience from non-Portuguese speaking countries. So first of all, I want to thank you, Mauro, for the very nice introduction. Thank you very much. And also I would like to thank and congratulate the organizers of this seminar, which has been very successful. This is the seminar number 57. And all the time with very interesting talks and very interesting and important foreign guests. So I have to say that it's really nice to see a successful enterprise like this one go on time. So congratulations to the organizers. And once again, thank you very much for your kind invitation to give a talk here.
César,
this work I will be talking about today is joint work with colleagues Leonardo Kozlov, currently at Case Western Reserve University in the United States, and Gabriela Planas from Unicampi. Before just going into the talk, let me tell you a very short story about what I will be talking about. With Leo and Gabriela, we started discussing a problem, which I will introduce soon. We then realized that we didn't know some estimates we needed for trying to solve that problem. Then we looked in the literature, and those estimates were unknown. So we decided to resolve that problem. But in the end, we could not, or we haven't been able to solve the original problem yet. But these estimates that we obtained in the meantime are very interesting because they may be, and they are useful for solving some other problems. So that's very typical of math research. You start trying to solve something, you cannot, and you end up solving some other problem, which also gives you ingredients for trying to solve new problems. So in some sense, we were very lucky about that happening. So let me introduce the main idea. After collaborating with Gabriela for some time and with Leo as well, we were very interested in studying geophysical flows. Geophysical flows are those that arise when you try to model the motion, for example, of a circulation of atmosphere or of sea currents using either the Navier-Stokes or Euler equations. And however, as you want to model real objects, which later can be modeled numerically or observed, and you have to, or you may be able to compare your results, your mathematical results with those real measurements, you have to take into account that the order of magnitude of the terms in your equation really matter, right? So from that point of view, for example, if you are considering rotating a rotating planet like Earth, well, for example, we have that the average velocity or the typical velocity in the oceans or in the atmosphere is the order of tens of kilometers per hour, while the rotation, the Earth rotation speed is roughly 1700 kilometers per hour. So whatever your term in your equation modeling the rotation is, it should be larger in some sense than whatever you have for your velocity u. And that fact must be reflected in the equations that you study, in the results that you study, if you want your equation to somehow model up, or at least approximately, the phenomenon that you're studying, right? In this particular case about the rotation of the Earth, well, we have the Coriolis force. We already know that from basic physics in high school, which is this fictitious force arising from a rotation around a fixed axis. So then that makes two things for us. The first one is that now there is a preferred direction. You have an axis of rotation, so then any kind of radial symmetry is destroyed by this anisotropy of the Coriolis force that should be related to this axis of rotation. So then the second thing is, well, we have to modify the Navier-Stokes equations, which with a new term that takes into account this rotation. So which is this equation? Which is this new equation? Well, as you see, the equation I have here is the Navier-Stokes equations for a homogeneous fluid, a fluid with constant density, a fluid which is incompressible, which is given by the divergence of u equal to 0 condition. And now we have, well, u is the velocity of the fluid, and I'm working in the whole of R3. I'm working with a three-dimensional fluid. Mu is the viscosity, which is multiplying here the Laplacian. Here is the vector Laplacian. We have the scalar P, which is the pressure. And we have this extra term here, omega times E3 cross U. E3 is the vector 0, 0, 1, right? So we're taking the cross product of that rotation, that's the axis of rotation, 0, 0, 1, with the velocity u, and we're multiplying by this positive constant omega, which I take to be larger than 1, really larger than 1, right? This will appear in an explicit way in the existence results that I'm going to quote and I'm going to cite, but also at the same time, this makes, this is coherent with the fact that I was saying, well, rotation, the speed of rotation of the Earth is really much larger than the average value that you might expect for, say, velocity of the vector field u, okay? Well, so then let's go on. What are the consequences of fast rotation in a fluid, right? One of the consequences is a very, very nice theorem known as the Taylor-Proudman theorem, which says, I'm going to read what I just wrote here, in steady, homogeneous, inviscid, incompressible fluid, for a small ratio of inertial to Coriolis forces, that ratio is called the Rossby number, the velocity does not depend on the component parallel to the rotation axis. So we have a fluid, even though the vector field lives in R3, the velocity of the fluid depends on only two variables. Let me show you now what I just said. What I wrote here is the Navier-Stokes equations, and now I started crossing out terms that I do not consider. Our flow is steady, so it does not depend on time. So this term, the derivative on time, if you dies. The fluid is homogeneous, fine, there's constant density. The fluid is inviscid, so there is no viscosity. Viscosity is 0, so this last term on the right-hand side here cancels. The fluid is incompressible, which you already have. Now we have a small ratio of inertial to Coriolis forces. The Coriolis force is reflected here in this new term omega E3 cross U. And the inertial forces are coming from U grad U, as we know from Navier-Stokes and Euler. So this one, the term with E3 cross U, is much larger than U cross U. So then we can cross this one out too. So then we're left with gradient of the pressure plus omega E3 cross U equal to 0. We take curl on this equation, and then using some, well, this curl of the gradient, which is 0, and then you have the curl of a cross product. Then we use some properties, and then we obtain this equation here, E3 dot nabla U equal to 0, which written in components means that for each component of the vector field U, the derivative with respect to the third variable is 0. In other words, each of the 3 components of your vector field depends only on 2 variables, the first 2 ones, right? So roughly speaking, I have a 3 vector field in R3, which is 2D, depends only on 2 variables. Kind of interesting, right? But well, you may say, well, okay, you impose a lot of conditions, but something interesting has to happen with so many, with such complicated ansatz. Let me show you that you can really experimentally measure or see the Taylor-Proudman theorem. And notice, a vector field that solves this equation depends only on 2 variables. So roughly speaking, if I take a point on the plane x3 equal to 0, the vector field evaluated at x1, x2, 0 determines all the vector fields at x1, x2, whatever the third coordinate is. What do I mean? Let me show you. I will try now to do the following. I will show you some pictures, and I will click on one of the pictures. I will go to a video on YouTube. And most likely there will be some advertisements for, I don't know, decolar.com or some other company. We will have to wait for 5 seconds for this one. But look, take a record player and put a flask full of water in it and start spinning. Here, this, what I'm pointing out right now, is an obstacle, a disc, a metal disc at the bottom of this flask. So at the bottom, the vector field, the velocity field of the water is 0 at these points because there is an obstacle, there is no velocity there. So the Taylor-Proudman theorem tells me that all above this disk, the velocity of the vector field should be 0 too. So there should be no motion in here, which is kind of funny. It's interesting. So then what will happen? This flask will be rotating at a constant velocity with 33 RPM, right? And then you drop some ink, green ink in this case, and then you give a little bit of an acceleration, and then we will observe that the ink avoids, it doesn't enter the column, the Taylor-Proudman columns, above this obstacle that we have here. You see, you have here at the bottom, right? And then once that the ink starts moving, because there is a little bit of an acceleration, it avoids entering the column above this disk because the velocity above this disk is 0 because of the Taylor-Proudman theorem, right? So now I will try to do this. I will click on the image here. We will go to YouTube, and then we will see this video, which was made by the Fluid Mechanics Lab, Spin Lab at UCLA in California. Let's hope it works. It's coming here. It's taking a little bit longer than I expected. Here it comes. Okay, let me stop it. You see, the ink here is moving because there is an acceleration. We have the top view up here and the side view on this side. All right, let's keep on going. You see the ink starts moving because of the acceleration, but it does not enter this column. It's a virtual column. There is no physical boundaries. The vector field knows that, the fluid knows that above the bottom, above this obstacle, the velocity has to be 0 because the velocity is 0 at the bottom, right? So then the ink has to go around and it cannot enter that Taylor-Proudman column. Okay, so this theorem really explains things. It really works, right? All right, so this is it was made at the geophysics program at the Department of Earth, Planetary and Space Sciences in UCLA. So the theorem, the Taylor-Proudman theorem, really works. We are back now, okay? Now, well, what I did was I dropped lots of terms, but what if I keep them, right? I mean, if I drop all those terms, the DTU term and the inertial term, then I obtain a 2D flow in R3. But then, what if I keep these terms? Well, that's asking the question of how 2D is a Navier-Stokes-Coriolis flow. Right now, I will be in 3D. Now, my solutions will have depend on 3 variables. But will they be 2D in the end? Will they approach their 2D counterpart? Well, how you do that? Well, you solve the 2D Navier-Stokes in R3, and you take a 3D perturbation, and then you solve 3D Navier-Stokes-Coriolis and see what happens. From the mathematical point of view, Chemin, Desjardins, Gallagher, and Grenier did that. There are lots of information here. Let's take a look at this equation for W here. W is the difference between U, which is a 3D Navier-Stokes-Coriolis, and U bar, which is a 2D Navier-Stokes. And I'm trying to measure the difference between the two. The difference between the two is W. You can prove that if the initial data is incompressible and in H dot 1/2, then you have solutions. You have weak solutions. And those solutions are, this is a very important point. This is the main point for our question. The solutions are continuous in time and bounded in H dot 1/2. Okay? But to be fair, this H dot 1/2 norm should go to 0 with certain rates. But you should ask, why you ask this question? Well, because for Navier-Stokes equations and Navier-Stokes-Coriolis equations, we supposed this is true. The norm of the solution goes to 0, right? So then this is the question we try to answer with Gabriela and Leo. Does the H dot 1/2 norm go to 0 here? Well, for doing that, we needed to know what happened to the 3D Navier-Stokes-Coriolis equations. And we thought, oh, this should be known. This must have been done already by someone. Well, the thing is, that's not the case. So then that's how the story started. First, now, let me remind you, what does it mean for, how do we have this idea, okay, that solution should go to 0? If you have the Navier-Stokes equations, like here in Rn, but in particular in R3, as we're doing here, you can show that the L2 norm goes to 0, that Kato and Masuda did in the mid-80s, right? The initial data is incompressible and in L2. In a very important work, slightly later, Maria Elena Schombeck showed that if your initial data is a little bit more concentrated, it is in LP intersection L2 with P greater or equal than 1, then you can have an algebraic decay rate, which depends on P, of course. P is how concentrated your initial data is, right? Why so? Why does it happen? Well, it happens because if you take the heat equation, you can see that the decay rate is determined by small frequencies of the initial datum. Just take the heat equation, solve it with Dirichlet boundary conditions. You have U0 as initial data, and then you can explicitly write, oh, hey, this is the heat equation. This is calculus 4 for our engineering students. You can explicitly write a formula for the L2 norm depending on T, which is exponential of minus 2k squared T times the coefficient of the Fourier expansion of U0, okay? So as you see, these are exponentials, and the only one that you will observe in the long time is the one with the smallest k, which is, of course, multiplied by this frequency here. But if this is 0, then you will observe the next one. So roughly speaking, what you will observe here as a function of t is the exponential associated to the first non-zero coefficient of the Fourier expansion of U0. Okay? Well, but if you do that in Rn, then you are in trouble because the Laplacian has no smallest eigenvalue or things like that. But then what you do is that what Clayton Biolan and Maria Elena Schombeck did, and then Maria Elena and myself and Lorenzo Brandolese extended, is to initial data U0 in L2, we can associate a number which roughly speaking measures the algebraic order in frequency space of that initial data. And it gives a number called the decay character, R star. And that decay character, R star, allows us to show that for the heat equation, you have upper and lower bounds which have the same exponent. So they have pretty sharp estimates. When you go to the Navier-Stokes equations, that's where I'm now, what you can do is that you can show that now the L2 norm of the velocity, the kinetic energy, decays like either minus 3/2 plus R star or minus 5/2, right? When R star is, again, the decay character. So you look at the decay character and you know how it will decay. And also we know that if R star is less or equal than 1, then we have the corresponding lower bound, right? So this is work by Clayton and Maria Elena and by Maria Elena and myself. So you see, this is a very, very good thing because before you had to put conditions, extra conditions, and you had to study case by case the decay of the solutions. And now with the decay character, we can study all of them all together at the same time. And moreover, you can compare because if R star is less or equal than 1, the decay is the same as the heat equation, right? But then if R star is larger than 1, the decay equation decays too fast. I'm sorry, the heat equation decays too fast, and the nonlinear part is the one that decays slower. So then the decay character is a very interesting tool, right? That was in L2. Now let's go for Navier-Stokes and decay in H1/2 and H.1/2. H.1/2 is one of the Sobolev spaces that we wanted to study originally from that problem inspired by the result of Chemin de Jardin, Gallagher, and Grenier. And here things are different because there are no decay results in H1/2, right? So the H1/2 norm, you do not know if it has a decay rate or not. There are some technical issues, right? If your initial data is in H.1/2, you have mild solutions, but the only thing you can say is that the limit of the H.1/2 norm is 0. You cannot say if there is a decay rate or not. That's resolved by Gallagher, Iftine, and Planchon. These are the kind of results that we need for studying the original problem. So we don't have them. So we have to solve that problem. And now go for Navier-Stokes-Coriolis, which we also need, right? Well, for Navier-Stokes-Coriolis, the situation is pretty much the same. Maria Elena Schomburg and Jeff Vallis studied a Navier-Stokes-Coriolis-like system in which they coupled with the Boussinesq equation, but it's not good because the Boussinesq part decays exponentially. It pulls everything really fast to zero. But if we decouple things, you cannot say anything about Navier-Stokes-Coriolis. So no results. If the initial data now is in H1/2 for Navier-Stokes-Coriolis, the only thing you can say is a result by Huber and Shibata is that the H1/2 norm is bounded, period, not even go to zero. And if the initial data is in H.1/2, then Iwauchi and Takada prove that you have mild solutions, but you see once again, we have that the solution is continuous in time in H.1/2, but no decay, not even going to zero, right? So all the results that we would need for proving the result that we wanted to prove, we don't have them. So we have to prove them. So that's what I was saying at the beginning. We wanted to solve a problem. We need some results, which we thought they were well known. They're not. So let's go and prove those theorems. What did we prove? We proved that for the Navier-Stokes equations and the Navier-Stokes-Coriolis equations, in the critical space H.1/2, I will say soon what does critical mean. And in the Sobolev space H1/2, there is decay. The decay will be given in terms of the decay character. A very, very important point here is this that I'm showing you right here in the middle. In H.1/2, both for Navier-Stokes and Navier-Stokes-Coriolis, the decay is the same as the heat equation, right? This is the first time that this phenomenon is observed for a nonlinear equation. The fact, of course, is that it's a critical space, right? I will talk about a little bit later, right? And the main idea behind the proofs are somehow the standard ones. We first have to show that the H.1/2 norm is a Lyapunov function. Then we have to find some rigorous a priori estimates, and then we can use the Fourier splitting method and the decay character in the way in which was developed by Clayton and Maria, and then by Maria Elena and myself and Brandolese. This is the big picture of our results, right? So now let me tell you about this very interesting H.1/2 space, right? This H.1/2 space is critical. Why? Because the H.1/2 norm is invariant when I scale it with the usual scaling that we use for the heat equation or for the Navier-Stokes equations, which is this one right here, right? And right down here, I am writing that the H.1/2 norm of U and of its scale U sub lambda is the same. There are a bunch of existing results of global mild solutions for the Navier-Stokes and Navier-Stokes-Coriolis equations in this H.1/2 space. There are some technicalities over here that I don't want to go through them right now, because I want now to state the result, the first of the results that we proved with Leo and Gabriela. Initial data in H.1/2, divergence free, and with small norm, right? And this U0 initial data, it's in H.1/2. So the gradient of U0 is in L2, so it has a decay character. That decay character is R star. So then we can prove that the H.1/2 norm of the solution decays like T to the minus 3/2 plus R star. The result by Gallagher, Iftine, and Planchon said, the only thing that said is that, well, this norm goes to zero. Now we can say that, yeah, it goes to zero in an algebraic way, right? And now here comes the point that I was just telling you about. This decay is the exact same thing as the decay of the heat equation. So in some sense, the nonlinear term does not play a role, which makes perfect sense, because if you have this, if you're in this h dot 1/2 space, which is critical, which is scale invariant, if it's scale invariant, none of the two terms, either the linear part or the non-linear part of your mild solution, should be bigger than the other one. So then both of them have the same behavior in terms of decay. And you see, compare with what happens with the L2 decay for the Navier-Stokes equations. In the Navier-Stokes equations, when R star is less or equal than 1, you have this decay right here, 3/2 minus 3/2 plus R star, which is the decay of the linear part. But if not, then you have this decay like minus 5/2, which is decay of the non-linear part when the dissipation is really fast. Now, I'm sorry, this was for the Navier-Stokes equations, Navier-Stokes, okay, right? Now we have this pretty much the same result for Navier-Stokes-Coriolis, which improves, now we improve the result by Iwauchi and Takada. They only showed that this norm was bounded. They could not even prove that it goes to 0. We prove that it goes to 0 with this algebraic decay. There are some technicalities here concerning the size of the initial data and the speed of rotation. As I'm kind of short of time, I will not go very deep into that, but those kind of things are very common in equations in which you have a very strong dispersive component, as Navier-Stokes-Coriolis has. Okay, dispersive people that are watching this talk right here should think, oh, the size of the velocity of the speed of rotation that you need does not depend on the norm of U0, but on the profile of U0. That's what I'm talking about. But now that was for these two results were for h dot 1/2. Now let's go for h 1/2, right? Now it's not more the homogeneous Sobolev space. Now it's inhomogeneous. And well, there are plenty of existing results for Navier-Stokes. Some of them go back to Fujita Ikato in the 60s. And there are for Navier-Stokes-Coriolis, which are more recent, right? And there are conditions on the initial data, on the size, right? But then for Navier-Stokes equations, we get the exact same results that we should expect. They are analogous to the Navier-Stokes equations. And for the Navier-Stokes-Coriolis equations, we get the exact results that we should expect when compared to Navier-Stokes. Here, things are more similar to Navier-Stokes and Navier-Stokes-Coriolis than in the case h dot 1/2, which were pretty different. Let me give you a basic idea of how the proof goes. It goes like this. I'm sorry, here. First, you have to show that the h dot 1/2 norm is a Lyapunov function, so the function is decreasing. Now, this allows us to show this equality in a rigorous way. You see, we have the derivative in time of the h dot 1/2 norm equal to minus the h dot 1/2 norm of the gradient, right? Minus this other term, which has no sign. It could be either positive or negative. Well, we go through some inequalities and we end up with this last line. You see, if this factor inside the parentheses were a positive number, then we are in a good position, because we will have that the derivative on time of the h dot 1/2 norm is minus a positive constant times the gradient of u, and then we should be able to start using the Fourier splitting method. But here comes the point. Our solution, u, is obtained through a fixed point theorem. So as is obtained through a fixed point theorem, this quantity here, u of t h dot 1/2, is uniformly small, because it's a fixed point theorem. You are in a ball around your initial data of a small size. So if you take that ball small enough, you need to take the ball small enough for having fixed point, for you to be able to apply the fixed point theorem. And then this will be small. So then constant times this quantity will be uniformly small in time, less than 1, if you shrink that ball enough. And then you obtain this inequality like this. Now you can use the Fourier splitting method developed by Maria-Elena Schomburg in the mid-80s for Navier-Stokes equations and for dissipative conservation laws. And you obtain this funky inequality right here. But you see, inside of the parentheses on the left-hand side, we have the norm that we want to estimate, and we have the derivative, and we have this integrating factor. We integrate the whatnot, but in the end, you see the only thing we can estimate, we have to estimate, is this quantity, the integral in a ball B of t, where the radius of the ball is a small one, it shrinks, it decreases on time, and then we have to go through this pointwise estimate in Fourier space for this quantity. This is how you use Fourier splitting, right? I'm not saying that the estimates here are easy, they're not terribly difficult too, but you have to take care of them, right? So then once that you do that, you solve the problem and you have an upper estimate for this h dot 1/2 norm, or for the L2 norm of the gradient 1/2 of this solution, right? But there are some things right here which I did not give the details, but I would like to mention them right here. So I swept them under the rug, but in the paper everything is fine, everything is proven, right? First of all, the Navier-Stokes-Coriolis semigroup has some dispersive properties which are delicate. And if you want to use that semigroup, you have to be careful in what you do, right? This dispersion part comes from the rotation, from the E3 cross U term, right? So then that's one point that you have to be careful about. And that's the reason why there appear, like in many dispersive equations, these conditions on the fixed point theorem working, but not in terms of the size of the initial data, but of the profile of the initial data, right? Dispersive people know what I'm talking about very well. The spaces in which you use the fixed point theorem are kind of not very intuitive, but after you think about them a little bit, then you find that they're the right spaces, okay? So, and on top of that, from the definition of these spaces in which you use the fixed point theorem, you can infer properties that you need for the estimates that we're trying to prove, right? All these results, we took them from different sources, right? There were already existing results in h dot 1/2 and in h1/2 for Navier-Stokes and Navier-Stokes-Coriolis. So the only thing we had to do is carefully study where these fixed point theorems were applied in order to be able to prove our results and use these properties. Right. Then we wanted to use the Fourier splitting method and the decay character, okay? Then we run into trouble because the semigroup associated to Navier-Stokes-Coriolis, it does not fit in the framework of the linear parts for which we have result for the decay character, right? For having result for using the decay character, you have something that looks like the Laplacian and something like behaves like the Laplacian, right? So it has to be positive semi-definite. That's not the case for the linear part of the semigroup of Navier-Stokes-Coriolis. So we cannot use those results by Maria-Elena Schomburg and myself concerning the characterization of decay, upper and lower bounds for the linear part. We cannot use them. So we have to modify the arguments in that proof in order to use these results here for Navier-Stokes-Coriolis specifically, right? And then when you use the Fourier splitting method, in general, what you do is the following. You find some L2 estimates, and then you use these L2 estimates for obtaining a decay for the derivatives of the solution. However, if here we are in h dot 1/2, we don't have an L2 part, right? So then we have to do things by hand, in a somehow very straightforward way, but not a total trivial way. And then we have to bootstrap and do things. But what saves the day is that we are in the critical space. The critical space, the one which is scale invariant, those spaces are particularly good for using fixed point theorems, right? And also for using some type of Holder estimates in which everything looks nice. You plug something on the left-hand side and then you use Holder, and then things that come on the right-hand side are the right ones that you need to use, right? The critical space is beautiful. Now, well, what happened? We started with a problem that we didn't know how to solve. This one, because we needed estimates for this U bar and for U, which solves the 3D Coriolis, Navier-Stokes-Coriolis equation. Okay, now we have those estimates, and now we can go back trying to solve this problem. So now we can try to show that W, the H dot 1/2 norm of W, goes to 0. We're still working on it because there are some subtleties concerning the interaction, because remember, U bar is a vector in R3, is a vector field in R3, but depends on only two variables, x1 and x2. And U is a real 3D vector field in R3. U depends on x, y, and z. So then there are some subtleties here, and we're still working on trying to show that W, the H dot 1/2 norm of W, decays. So, well, from that point of view, not so successful. Well, we proved those results, which are really interesting and which were unknown, and in my opinion, are rather important. But moreover, we got something else. The method that we use in the critical space H dot 1/2 for Navier-Stokes-Coriolis, if you look at it, the key point is that you're in a critical space, right? So everything comes out nice. Holder inequalities, estimates, lots of things, they work because you're in the critical space, not because it's Navier-Stokes-Coriolis equation. So then we said, hey, let's try some other dissipative equation in a critical space and see what happens. And let's try to use a method. Find a mild solution in this critical scale invariant space, prove that the norm, the critical norm, is a Lyapunov function, and then use the Fourier splitting method and use the decay character. Well, the first one that we came up with is the very well-known nonlinear heat equation with a critical nonlinearity, right? Here in R4, the critical term is absolute value of U squared times U, initial data in H dot 1. This H dot 1 is the critical space, right? This equation is has been studied a lot, and there are subcritical and supercritical counterparts. They have been studied a lot, and it is well known that there is this ground state, this stationary solution, which is very symmetrical, right? So this W is a solution, is a stationary solution to U. This equation here has a natural energy, which is this 1/2 of the kinetic energy minus 1/4 to the L4 norm, or this H dot 1 and L4 part. The energy and the kinetic energy are scale invariant, as before, because this heat equation has a natural scaling too. So if I scale them, both the total energy and the H dot 1 energy, the kinetic part, are invariant. So then we are in good shape. And we have that Gustafsson and Roxana's prove that if you're below, if your energy, the energy of your initial datum, and your kinetic energy of your initial data are smaller than the corresponding energy and kinetic energy for that stationary solution, which are called the Owen-Talenti bubbles. Then you have a unique solution, and then the energy, the kinetic energy, goes to 0. Well, with our method, we can prove not only that it goes to 0, but that it has a decay rate, once again. Aqui a gente tenta usar e consegue usar o mesmo método que a gente usou para Navier-Stokes-Coriolis. Por quê? Porque a energia e a parte cinética da energia, as duas são invariantes para a mudança de escala, ou seja, o espaço H.1. Oh, desculpa, estou falando em português. I'm sorry. The energy and the kinetic energy, both of them are scale invariant. It is known that for initial data, such that they are below, in the sense that their energy and their kinetic energy are below the one for the stationary solution given by the Owen-Talenti bubbles, then there are global solutions, and that goes to 0. But moreover, we can show with our method that not only goes to 0, but it decays with this algebraic rate, right? So then what happened? We started trying to solve a problem. We needed some ingredients for that problem. We didn't know how to solve our problem without those ingredients. Those ingredients didn't exist in the literature. Those estimates, which are pretty important, nobody had proved them. So we had to prove them. And then we proved them, we came back to our problem, and we are trying to solve it right now. But the most important part to me is that we found that this method of finding solutions in these critical scale invariant spaces, proving that the Lyapunov function is, that the norm is a Lyapunov function, and they using Fourier splitting and the decay character to prove decay, this should work for many dissipative equations in the critical space. And for example, it works for this nonlinear critical heat equation in dimension 4 and in the critical space H.1. So hopefully now we will be able to use this method for many other equations, and we are starting to work on that. So thank you very much for your attention. Thanks a lot.
Obrigado, César. Estamos aqui aberto a perguntas. Alguém tem alguma pergunta ao César, por favor? Pode também escrever no chat. Bom, alguma pergunta? Juan, você abriu aí para as perguntas? Ok. César, eu vou fazer uma pergunta em português, tá? Henrique, você quer fazer alguma pergunta? Sim. Abre o microfone para o Henrique. Isso.
Yes. Okay. Thank you very much for your talk. It was very interesting. And I was interested in a similar problem in which there is a temperature coupled to the motion equation. So have you looked at the influence that can be by the heat flux? Does the heat flux any relevance in the behavior of the decay behavior of the variables?
It depends on the coupling that you have, because of the following. Think of the linear part of your coupled system, right? So you have the velocity u, and then which will be most likely you will end up with sort of the heat equation or the Stokes system. And then for the temperature, you will have something else. So then you will have, you go to Fourier space, and then you will have a matrix of symbols for these operators, right? If you can diagonalize this matrix, then you can use this method. And then you will be able to obtain decay. And what will happen most likely is that there will be an interaction between the decay character for the initial velocity and of the initial temperature. And that would be very interesting, because now think that these decay characters are kind of not controlled. I don't want to give an impression that this has something to do with control theory. You have now these plugs that you move in order for, okay, if the decay character is big, then dissipation is really, the dissipation of the temperature is really fast, and then the fluid acts more like just a transport, and then the decay will be such and such. We have not studied yet these kind of systems. There are in the literature some coupled systems, say, for example, MHD or magneto-micropolar things in which this idea is used, but in my opinion, it has this method has not been exploited enough in order to get more meaningful results. But just to be fair, you must work, this idea only works in Rn. You cannot use it in bounded domains. Bounded domains, decay will be always exponential because you will have kind of the Poincaré inequality, and that will be your first eigenvalue, and that will give you the exponential decay. But the short answer is, depends on the coupling that you have, and there are lots of work to be done in these coupled systems and trying to understand the interaction between the decay of the two parts, depending now on the decay character of initial data.
Okay, thank you.
Mais alguma pergunta? Ô César, vou fazer uma pergunta em português, tá? Eu percebo nessas equações que tem uma dependência muito forte do zero, da dependência do dado inicial. Então, se você tem o dado inicial bem limitado, aí você consegue o decaimento, quando o t vai para o infinito, dá o de t. Mesmo o teorema do Kozlov, que você mostrou aí para Navier-Stokes-Coriolis, ele também depende da forma do dado inicial. Quer dizer, qual é a ideia de generalizar isso? Quer dizer, se você pegar, por exemplo, o dado inicial em H ponto meio ou L2, esse é um ponto estratégico para vocês, não? Para ter esse decaimento?
Sim, é simples o seguinte, você tem o dado inicial entra no jogo de duas formas diferentes. Primeiro, a escolha do espaço de funções é importante pelo seguinte: os espaços que são invariantes por escala, como H ponto meio, são muito usados para procurar, por exemplo, blow-up de soluções, ou seja, soluções que existem só de tempo finito. Tá? Uhum. Então, tem toda uma enorme quantidade de trabalho. Estou falando Navier-Stokes, mas isso em geral, de estudo de Navier-Stokes em espaços invariantes por escala, porque tem essa importância, a importância de você consegue provar soluções que têm blow-up. Então, aí você está um pouco mais perto de saber, de resolver o problema do $1 milhão, por exemplo. Tá? Então, agora, como consequência do fato que você está nesse espaço de invariante por escala, o que acontece? Acontece que você ganha que você pode usar ponto fixo, tá? Para provar existência, porque nesses espaços, o operador da parte do ponto fixo é muito bom, ele é muito legal, todas as estimativas saem bonitinhas e você consegue usar ponto fixo. Tá? Então, a motivação física de você estudar o blow-up, que se dá, por exemplo, e também, por exemplo, na equação do calor não linear, é a mesma coisa. Abaixo do exponente crítico, você tem soluções positivas que têm blow-up. Acima do exponente crítico, você tem soluções definidas sempre para todo tempo, não tem problema. No crítico, o crítico é onde as coisas interessantes acontecem. Então, por isso você estuda esse espaço. Por outro lado, aí o espaço crítico deixa você usar ponto fixo. Mas, agora, se você usa ponto fixo, você vai pedir que você vai precisar que o dado inicial seja pequeno. Uma coisa importante do nosso trabalho é o seguinte: as pessoas que fazem ponto fixo em espaços críticos, não usam Fourier splitting, porque Fourier splitting você precisa passar no espaço de frequência. Então, você precisa de um espaço de Sobolev, um espaço que esteja baseado em L2. E as pessoas que fazem coisa no espaço de frequência, raras vezes usam os espaços críticos, porque os espaços críticos, só alguns são Sobolev. A grande maioria são outras coisas. Tem alguns versos aí também que você pode fazer. Então, a gente está pegando ferramentas do mundo e usando com os resultados de existência e os métodos do outro mundo. Bate, por quê? Porque é um espaço crítico que é um Sobolev. Então, acho que essa é a coisa mais importante que eu gostaria a mensagem de passar, por que o método funciona e por que funciona para Navier-Stokes-Coriolis, para Navier-Stokes, agora para a equação do calor não linear, poderia funcionar para sistemas acoplados, como aqueles para os quais Henrique perguntou. A gente tem que encontrar qual é o espaço crítico desse sistema, ter solução mild, solução integral, NRN, e depois estudar. Eu tenho certeza que vai funcionar, porque o método que a gente achou é, assim, é perfeito para espaços críticos.
Ok. Obrigado, César. Mais alguma pergunta ao César? Bom, César, então quero agradecer a sua presença aqui, muito obrigado, parabéns pela sua palestra, calma, tranquila, e sucesso para você. Então eu vou passar a palavra agora para a Sandra. Sandra, por favor.
Alô? Vocês
Oi.
estão me ouvindo bem?
Sim, muito
que
bem.
Eu tive um monte de problema enquanto aqui caiu tudo. Muito obrigada, então, obrigada ao César, realmente, pela palestra, e ótima palestra, e a todos que estão aí nos ouvindo.